Let's talk about something that powers pretty much our entire world, but is completely invisible. Yeah, I'm talking about electricity. It's in the device you're watching this on right now. It's in the lights above your head. It is literally everywhere. But how does it actually work? Well, we're about to find out.
So here's a weird question for you. What could a massive, chaotic lightning bolt and your super precise smartphone possibly have in common? I mean, one is this crazy burst of raw, natural energy, and the other is a piece of tech we control completely. But believe it or not, they're both run by the exact same set of rules. And by the time we're done here, you're going to see exactly what I mean.
Okay, to make this whole invisible electricity thing visible, we're going to use a really simple but honestly a super powerful mental trick. I want you to forget all about electrons and circuits and weird physics just for a few minutes. Instead, just picture a regular old garden hose with water flowing through it. Seriously, this one little analogy is the key to getting all of this.
So on one side, you've got electricity, right? This invisible flow of these tiny little things called electrons. On the other side, you've got something we've all seen a million times, water flowing through a pipe. From here on out, every single time I say electricity, I want your brain to just swap that word out and picture water in a hose. Trust me, this little switch is going to make everything click into place.
You know, the story of electricity really just boils down to three main characters. They all work together as a team. Their names are voltage, current, and resistance. If you can understand what each of these three does, you basically understand how electricity works. It's that simple. So let's meet them one by one.
First up to the plate is voltage. The easiest way to think about voltage is that it's the push, it's the pressure, the force that gets the electricity moving to begin with. If you don't have any voltage, nothing is going anywhere. It's basically the get up and go of the entire system.
And this slots perfectly into our water analogy, right? The push from the voltage is just like water pressure. So imagine you've got this big water tank way up high on a tower. The weight of all that water creates a ton of pressure, and that pressure is what forces the water down and through the hose. Well, that pressure is our voltage.
And, of course, we measure this electrical pressure in a unit you've definitely heard of before, volts. You know when you see a 9-volt battery? That number, that 9V, is literally telling you how much electrical push that battery has packed inside it. Okay, so if voltage is the push, then our second character, current, is the actual flow. Current is how we measure how much electricity is actually moving through the wire. It's not the pressure behind it, it's the stuff itself that's in motion. So back to our hose. Current is just the flow rate of the water. You know, how much water is actually coming out of the end of that hose? Is it just a tiny trickle, or is it a gushing fire hose? That amount of water moving past a certain point every second, that is the current.
And we measure this flow in something called amps, but pretty much everyone just calls them amps. So next time you look at your phone charger and it says 2 amps, you'll know that's not about the pressure. It's telling you about the rate of flow of electricity it can deliver.
And that brings us to our third and final character, resistance. See, in any system, there's pretty much always something that's trying to slow things down. And in electricity, that's resistance. Think of it like electrical friction. It's anything that gets in the way and opposes that flow of current. And the water hose analogy for this one is just perfect. Resistance is like putting a kink in the hose, or maybe the hose suddenly gets super narrow. The moment you squeeze that hose, you are resisting the flow of water, right? It gets harder for the water to push through. That's a perfect picture of what electrical resistance does.
We measure this electrical squeeze in a unit called ohms, and its symbol is the Greek letter omega. So it's pretty simple. The more ohms something has, the more it's going to fight back against the electrical current trying to get through.
Okay, quick recap. We've met our team. Voltage is the push, current is the flow, and resistance is the squeeze. But here's the cool part. They don't just do their own thing. They're all connected, locked together by this one beautifully simple rule that governs pretty much everything in electricity.
And that relationship is captured in a little something called Ohm's law. Think of it as the secret handshake of electricity. It just says that voltage equals current multiplied by resistance. V equals I times R. That's it. This one little formula is the key to understanding how they all work together.
Let's make this ridiculously simple with our water hose. Step 1. If you increase the pressure, that's the voltage, what happens to the water flow? Well, it goes way up, right? More push means more flow. Okay, step 2. What if you keep the pressure the same, but now you kink the hose, you increase the resistance? The flow obviously goes down. So it's totally intuitive. Current goes up when you add more voltage, and it goes down when you add more resistance. It really is that simple.
So what's the big idea here? What's the main takeaway? Well, we started with this totally invisible force, and just by using one simple analogy, we can now basically see exactly how it all works. Just remember this. Voltage is the push, just like water pressure, and we measure it in volts. Current is the flow, just like the water's flow rate, and we measure that in amps. And resistance is the squeeze, like a kink in the hose, measured in ohms. If you can remember that, you've totally got the fundamentals of electricity down.
And that leaves us with one final thought. You know, we usually think of resistance as a bad thing, something we want to get rid of, but it's not. In fact, we use it on purpose all the time. So here's a question for you. What's something in your home that is designed to have super high resistance in order to do its job? Think about things that get really hot or that glow, like a toaster or the tiny filament in an old school light bulb. They work precisely because they resist the flow of electricity so much that all that friction makes them glow red hot. See, the fundamentals are everywhere once you know what you're looking for.